Hello everyone, welcome to topic 6.6, Introduction to Enthalpy of Reaction. By the end of this, you should be able to calculate the heat absorbed or released by a system undergoing a chemical reaction in relationship to the amount of the reacting substance in moles and the molar enthalpy of reaction. So, heads up, this is thermodynamics and stoichiometry together. But as long as we can be able to read the units of the values given to us, we can use them the same way we have used previous stoichiometric quantities. Okay, so let's look at how we can do that. As we have seen, many reactions lose or gain energy as a reaction takes place. This can be represented in different ways. So for example, we have this reaction given here, and we see that we have this delta H provided. Right? So this is the energy associated with this specific reaction. Because it is a positive value, we see this plus sign right here. That means that it is an endothermic process. Okay? That means that it is being added to the system, so it is acting as if it is a reactant. So if it's an endothermic process, energy acts as though it is a reactant. So we can write it on the reactant side. So both of these reactions indicate that the reaction is endothermic, that heat is absorbed. The reaction shows the amount of energy required for the reaction as it is written. 1 mole of each reactant to form 2 moles of the product. The heat can therefore be used as a conversion factor, remember stoichiometry, as shown below. Okay, so here we have how much heat is required to react at 2.4 moles of N2 with excess O2 to form NO. So we can use our starting quantity here and the heat of the reaction. So this is from here. Okay, so this is per 1 mole of technically the reaction, but because there is a 1-to-1 ratio, if I could erase that, because there is a 1-to-1 ratio for how many N2 are involved in that reaction, you can omit that part. You will not see me do that because technically the units, the units should work out so that the units match what we're using here. So moles of N2, 2 moles of reaction, and then your 1 mole of reaction, or for every reaction, you have 180 kilojoules, where this should be 1-to-1, and that's why you could omit this middle process and just nix these and shove it together. However, we see that that is not always going to be the case, and so it is more valuable to you in the long run to actually not skip your reaction here. However, they do show you here that you can substitute in however many moles for the reaction with the moles of the substance you're talking about. Okay, so we have a couple different examples here for you. Okay, so please note that at constant pressure, which is common for most AP reactions, delta H is equal to Q. And we have a little walkthrough here showing you how energy and work cooperate in this to give us the fact that delta H is equal to Q at constant pressure. That's what that little subscript P is. So first law of thermodynamics says that the change in the energy of system is equal to the sum of the heat and the work done within the system. And so we can then substitute and rearrange some things, that the heat or change in heat of the system is equal to the energy of the system plus the change in the work. And so doing a little bit of rearrangement, work is equal to negative P delta V. That is a gas expression. Substituting in for the things we know, we see that we can simplify that all the way down to here. Okay. So let's apply some of these. For the most part, you're just going to assume constant pressure. There is not a lot of constant volume problems given in AP, and thus this is why we are not addressing it. So if you were to react 7.5 moles of H2S with 9.34 moles of O2, how much heat would be released? Well, first we got to do BCA table, right? Because we've got two starting quantities of products. So BCA. And because I'm only needing to discuss my reactants, I don't need to do the BCA table for my products. So I'm going to put in how much I start for each one, 7.25 moles, and then 9.34 moles. I don't need to include the units because BCA tables only work for moles. So bringing down my coefficients, so -2 and then -3. I'm going to divide into both of these. So I do 7.25 divided by 2, and that gives me 3.63. And then 9.34 divided by 3 gives me 3.11. I'm going to use the smaller value to substitute into both of these because that'll put one of them at 0 and none of them at negative. Because if I put this one in, I would have a negative value for O2, and you can't use more in your reaction than you are provided. So we will put 3.11 for both of these. This gives me 0. And then on the other side, this gives me 1.03. Okay? So that tells me that the value I need to convert into energy units is going to be the amount of oxygen because it is limiting. So that's going to control how much energy I make. Or, yeah, release because it's negative. Okay, so we're going to use the 9.34 moles of O2, and we're going to change that into kilojoules using all of our values. So our first one, and because it's me and I prefer to do a full conversion, I'm going to change my moles of O2 to the 1 mole of the whole reaction, and then I can use my energy or heat of reaction to determine the total energy. So 1 mole of reaction, and use my delta H here, is negative 1120 kilojoules. So if I plug in and do the math for this, right, these cancel, I'm left with just kilojoules for my reaction. So this is going to be 9.34 divided by 3 times the negative 1120 kilojoules. You should get negative 3490 kilojoules is released. And the negative sign tells us it is released. If you forget the negative sign, you need to say is released. Okay, but the negative sign lets us know that that's happening. Okay, finally, our we do. So I'm going to get us to a specific point, like talking through it, and then you're going to take it over from here. So if you perform this reaction and 92.1 kilojoules of energy is produced, how many moles of water? So you're going to go from kilojoules to moles of H2O. How many moles of H2O are produced? So you're going to use the delta H here because that's got kilojoules and moles. And then your stoichiometric, whoops, not for H2, you want water. Your stoichiometric ratios to determine this. So I want you to pause the video and perform this conversion starting with this one. So that's your given. And you're going to change that into moles of H2O using the reaction and the delta H value. Please pause the video now. Okay, so you should have gotten 0.382 moles of H2O. Now you might have gotten a negative 0.382, and that's because you would have plugged in the correct value down at the bottom. But remember that this is released. This energy is produced or released, so it is an exothermic process, so that energy is leaving. So its technical sign is negative, which I did not give you at the beginning. So these two negatives give us a positive, because negative divided by a negative is a positive number. So our value in the end should be positive because you can't have negative quantities. Energy A negative or positive sign indicates if it's moving into or out of your system, if it's gained or lost. However, for like the amount of matter, you can't have negative amounts of matter. So using these concepts and examples, please complete the you-dos, check your work, and thank you for tuning in.